chapter 7, and last time we got into some really important sort of calculations and really conversions, and the couple that we talked about were Avogadro's number. Remember, Avogadro's number represents a mole of something, so 1 mole of anything will equal 6.022 times 10 to the 23. Remember that the units of Avogadro's number can change, atoms, or they could be molecules, depending on sort of the situation you're dealing with. And remember that Avogadro's number is sort of the conversion factor that we use to go between those two units. So if you have moles and you want atoms or you want molecules, Avogadro's number is your conversion. Opposite is true as well. If you have atoms or molecules and want to kind of go back to moles, then you're going to use Avogadro's number, obviously, going in the other way. It is a normal conversion factor. You could do 1 mole, whatever you're talking about, over Avogadro's number. Or again, you can flip it around like normal and put Avogadro's number up on top of your conversion factor. And again, you want to really take just a dimensional analysis approach to this. As we talked about, kind of keeps everything simple and the calculation not too bad. So remember that we only really do want to use Avogadro's number if it is necessary. And the way, again, you could determine if it's necessary is if you are asked to solve for something in atoms or molecules, or you have a number that's in atoms or molecules, you typically will use Avogadro's number somewhere along the way in that calculation. Again, if there's no mention, like some of the examples we did, we would want to just kind of leave Avogadro's number there on the side. Another conversion, which probably you'll use more than Avogadro's number, is molar mass. And that's a really big sort of conversion factor. And the units of molar mass are grams per mole. And where we get the molar mass from is really the periodic table. So for example, hydrogen 1.008, oxygen 16. It is these numbers that we see on the bottom of the symbols on the periodic table. That's the molar mass. And again, if you're doing it, for example, just hydrogen, its molar mass would be 1.008 grams per mole. You could again use that as a conversion factor. You could go 1.008 grams over a mole of hydrogen, or a mole of hydrogen over 1.008 grams. Typically speaking, when you pull that number off the periodic table, 4 significant figures is where you go with. And it's the number always stays with the grams part and is always per 1 mole of whatever you're doing. We also could do that for something that is a compound. And basically all we'll do is just basically add up all the parts. So here we have 2 hydrogens from the periodic table, each are 1.008 grams per mole. We have 1 oxygen, which is 16 grams per mole. And that'll give us a molar mass of water of 18.02 grams per mole, which you also, again, could use as a conversion factor by just flipping it around. So molar mass is really your conversion to go between those two units, grams to moles, or moles back to grams. That is the molar mass, again, from the periodic table, is where you get that from. The relationship between all kind of 3 of those units is we got kind of grams, we got atoms or molecules at one end, and it is moles that sort of tie both of those sort of extreme units together, if you will. Again, molar mass going in this direction, Avogadro's number going backwards, Avogadro's number, and then molar mass. So again, that is definitely a conversion factor we use a lot in chemistry. A lot of calculations coming up, or pretty much you start with taking grams and converting them to moles. So molar mass is used a lot in those types of situations. Any questions on that there? Yeah. The sig figs in terms of molar mass in general is kind of the general rule is 4 significant figures is typically what you go with. So you typically would pull 4 significant figures off the periodic table. Like I said before, depending on what periodic table we're looking at, there may be a lot more numbers than 4, and there may be sometimes less, but most of the time there's more numbers. So typically speaking, 4, and just in general, when you're done calculating, usually 4 is a good place to end up with the molar mass. Other questions? Okay. So one last thing that I just want to kind of go over in terms of this type of calculation that you do sometimes come across before we kind of move on to the last part here of chapter 7. And that is, let's just say we had 32.5 grams of C2H6, and we wanted to know how many carbon atoms are there. So in this particular type of problem, we're actually not looking for the whole thing. We're not looking for the C2H6 as a whole. We're actually just looking at part of it. We're really just looking at the carbon part. And we will need a way to go from like this entire thing to really just the carbon part of it. And the actual formula itself can be used as like a conversion factor to do that. So when we look at a formula like so, when we see these numbers on the bottom, they do represent the moles of each of those elements that are present. So actually from the formula itself, we can have a conversion factor that we could get to take us from like the whole thing to just like one of the elements that are present. So we could say, for example, in 1 mole of the entire thing, there would be just 2 moles of carbon. And again, that just simply comes from the formula and the number it goes with, right? We could also say in 1 mole of this entire thing, there would then be how many moles of hydrogen? There would be 6 moles of just hydrogen. And again, that comes from the actual formula and sort of the subscript that is there. Thank you. So this allows you to use a formula to really, like I said, kind of go from the whole thing to just maybe one of the elements that are present. Now, clearly, we could use each of those as conversion factors. We could put one on top and the other on the bottom like we normally do. And in this case, since we are looking for carbon, we will use probably this one here along the way in this particular problem. Now, before I could actually use that as kind of like a mole to mole conversion, I would first need to convert my grams here into moles so everything cancels out correctly. So I do need to kind of do the process of taking my grams of the whole thing here to moles of my whole thing. And then I could kind of go from moles of my whole thing to just moles of carbon and finally to atoms of carbon, right? By the way, since it says atoms of carbon, what other thing am I going to use along the way? I will have to use Avogadro's number somewhere along the way since we are looking at atoms eventually getting there. Really, this last step right about there is where I'm going to use Avogadro's number to go from moles to atoms. So the first part of it is that really I just need to kind of convert my grams into moles. So again, that's going to be the molar mass from the periodic table I'm going to need to get. And once again, if you look at the periodic table, you got carbon that's 12.01. You again have hydrogen as 1.008. So if we do the molar mass here for our formula here, we would do 2 times the molar mass of carbon for both carbons that are present. We would add it to 4 times the molar mass of our hydrogen for all 4 of them that are present. And in this case, that's going to give us a molar mass of, oh, not that, 2 times 12.01 plus 4 times 1.008. It's going to give us something like 28.05 grams per mole. And again, on your calculator, you got 28.052. So as the question was earlier, here I would just round the 4 sig figs. It's just kind of a good common practice. Remember that this is really a conversion factor, right? And we could use it as such. So we're going to start with our number that we have, which is 32.5 grams of the whole thing. We are then going to use our molar mass. And again, We want to go opposites, which means we do need to put grams on the bottom. So we'll go 28.05 grams per mole of C2H6. Again, these are going to cancel as we multiply here, obviously, and again, divide by what's on the bottom. And if you want to get an answer at this point, you can, but you don't necessarily have to, but I'll just get an answer. Well, maybe I'll punch it in right first and then get an answer. Still wrong. Try that. Third time's the charm here. So we got 1.158645, and I'm not really rounding at this point because I'm going to continue on with the calculation here. And again, you don't necessarily have to get an answer at this point. If you do, like normal, don't round too much. You know, I kept a few more digits than I probably need. At this point, we now have it in moles of the whole thing. And that's what's going to now allow us to use our conversion factor here to go from moles of the whole thing to just the moles of carbon. And again, we're going to go opposite. So if you're just continuing on, your moles would be up on top. Here, our moles are also up on top. And we would go opposite to cancel. So 1 mole of the entire thing gives us 2 moles of carbon. And again, that comes from the actual formula. And that is the conversion factor that's going to get rid of the whole thing and now really just leave us with carbon. And again, we're doing the same math here as we talked about, multiplying the top, dividing the bottom. So in this case, we're really just going to multiply by 2. And if you get an answer, which once again, you could do it all in one calculation, but I'll just throw a number up here real quick. And we got moles of carbon at this point. Yeah. How did I get which number? Oh, I did put 4 instead of 6. I don't know where I got that. I got that from the wrong formula, apparently. Let me just try that again. Thank you. That is definitely wrong. We'll just cut that out of the video. It'll be all right. You know, that was, thank you. It obviously should be 6. I could just say the classic, you know, I was just doing that to make sure you were paying attention, but, you know, I kind of screwed that up pretty badly. All right, so let's do a little bit of racing. Yeah, you probably don't need that number anymore. All right, so we want 6 there would be good. Yes. All right, we'll go 6 there. So I recognize I messed that up. All right, so try with 6 times 1.008 plus 2 times 12.01. This will give us the correct molar mass of about 30. Sounds a little bit better there, maybe. 0.07 grams per mole. That's going to put our 30.07 grams here, which will obviously give us a different number. So let's try the right number there. Thank you very much. So we got 1.080811 moles of C2H6. That hopefully should be right. There it is. So that's good. So we're now going to multiply that by 2. And now we're at 2.1616 moles of carbon. Also helps, I suppose, to do the right molar mass, I suppose, along the way. All right, so now that we have this, we're close to what we want, right? We're in moles of just carbon, but we do want atoms of carbon. So again, that is Avogadro's number that we could use for the conversion. And at this point, again, moles are up on top. So we would want to put moles on the bottom. And again, Avogadro's number here up on top. And this would be atoms of carbon because it's just carbon. And now we should get hopefully the right answer. I hope. 1.3, I'll go 0 times 10 to the 24 atoms of carbon. So there's a lot of carbon atoms there, even more now that I got the right molar mass, I suppose, what I had previously. Any questions on that there? So this is kind of a wrinkle that sometimes you might come across a question where, again, they may not be interested in the whole thing, just maybe one part of the formula. And again, you can actually use the formula as a conversion factor to go from the whole thing to just one of those things. Any questions on those steps there? The other, I think, important thing that we talked about last time as well, in terms of molar mass, remember that, again, if you are doing the molar mass for anything, the units are grams per mole, and that means 1 mole. So as we talked about before, if it's like in an equation and there's a coefficient, we do not take the coefficient into account when we do molar mass. It's just the formula by itself, like we talked about last time. So again, if there was this an equation and you had a 2 in front of it, the molar mass would still be that if you calculate it correctly. Again, we don't take the 2 into account, so it's always just based on the formula by itself. Other questions right now? All right, so what we're going to now talk about is actually putting together the few things that we've been talking about after equation and grams per mole. So we're going to do what is known as stoichiometry, and these are calculations that are based on the equation. And what it allows you to figure out are things like if you did this reaction and you started with a certain amount of reactants, you can figure out, in theory, how much products you should produce if everything went perfect. You could also do the calculation sort of backwards. Like if you actually did the experiment and you produced a certain amount of product, you could use the equation and how much product you produce and sort of back calculate and figure out how much you started with. So we're going to kind of use grams per mole. We're going to use balancing equations for these things. And really, when we look at an equation, the relationship we're going to use is based on the coefficients. And from the coefficients in the balanced equation, you could say, for example, that is 2 molecules of H2 react with 1 molecule of O2 to give you 2 molecules of H2O. But really, for stoichiometry, it is this relationship that we use, which is sometimes referred to as the mole-to-mole relationship. And again, it is just solely based on the coefficients in the balance equation. And that's where those numbers come from. You could say there are 2 moles of H2 react with 1 mole of O2 to give you 2 moles of H2O. The last thing is conservation of mass, again, because hydrogen on the left and hydrogen on the right weigh the same. You won't lose any mass along the way because you have the same elements. That's why we balance the equation. So let's take a look at sort of stoichiometry. And again, these are the common sort of questions that are asked. If you produce a certain amount of product, how much reactants did you start with? If you start with a certain amount of reactants, how much product you could produce? You could also do stoichiometry to answer questions like, if I have so much of product A or reactant A, how much of reactant B would I need to react with each other? And if I produced, so much of one product and there was another product, you could also figure out how much of the other products you would produce as well. So it allows you a lot of these sort of relationships, and that's what's known as stoichiometry. And the units for stoichiometry can really be any units, but we will most often, and probably only in this class, see kind of these two units used with it, which are grams and moles. And that is the conversion that we were just using. Remember that if we need to go from grams to moles, or moles back to grams, we're going to get our molar mass from the periodic table there, right? It's going to be the conversion factor that's going to allow us to do that. So the mole method is based on those coefficients being the moles of each of those. And really what stoichiometry is, and sometimes people freak out about it because it's a weird word and it thinks it's really, really hard, but it really is just a conversion factor. So instead of like looking in a book to find the conversion factor, where you find the conversion factor is actually from the balanced equation. And that's where you're going to get your kind of your conversion factor. And the reason you need that conversion factor is typically in these problems, they will give you information about one thing in the equation, but you're actually interested in something else. So you use the equation as a conversion factor from like A to B in the equation so that you can figure out, what you're looking to find, be that, how much you're going to produce or, how much you started with. These are the general steps for a basic stoichiometry problem. I would say probably for us, most of the time, step one is going to really be done for you. But just in case it's not, a reminder, like we talked about, maybe with naming and predicting products, you do want to make sure that before you even think about balancing an equation, that you have all the correct formulas down. So if you happen to be given everything in words, you got to turn those words like you were doing nomenclature into proper formulas, and then you should balance it. Probably the most of the time, you're just going to start with the balancing. So we could probably narrow this down a little bit. First step should always be a balanced equation. If you do not have a balanced equation, these calculations are pretty much not going to work out right for you. So If you have an equation given to you, you should make sure it's balanced. If you see coefficients, it's probably going to be balanced, but you just want to double check. The next thing you really want to do is take whatever they give you, whatever there is given to you, and whatever unit it is, and you basically want to convert those guys into moles. I would say probably 99.9% of the time, you're going to be doing at this point that grams to mole conversion we were just talking about. So you're going to use your molar mass to do that. Once you have everybody that was given to you in moles, you're then going to actually do the big stoichiometry part. And that part is you're going to go to the balanced equation and find the mole to mole relationship that you are interested in. So what would be the mole to mole relationship you're interested in? Well, the first thing you're interested in is whatever they gave you. So that's one thing you want to find in the equation. The other thing you're interested in is what you're trying to find. So those are the two things when you look at the equation you want to try to find. Lastly, if you do all these steps right there, that is the big stoichiometry move. You will be always sitting at this point in units of moles. And a lot of times they may want some other unit for the answer. So you typically have to convert that into some other unit. And I would say very common for us, maybe moles back to grams is a very common sort of ending. And again, that would be your molar mass. Now, mind you, you could be given like the second thing there in any unit, could be like maybe pounds or something like that. So you somehow want to get whatever unit they give it to you to grams, and then molar mass, grams to moles. And on the back end of the calculation on step number 4, you may be asked for some other unit besides grams. So you might be going from moles to grams and maybe grams to pounds or something like that. So there could be some other type of unit. But I would say very commonly moles, grams, grams and moles are typically the ones that you get there. So let's take a look. And really, if you follow these steps, as we'll do in some examples here, it should really lead you to the right answers. So the idea is you always want to kind of start at the first step and keep working your way through. If something is done for you, don't undo it and go backwards. Yeah, just go forward. Yeah. So step 2 is done for you, just go to the next step, right? And that's the important thing. So let's take a look at an equation such as this equation here. Now, from this one single equation, we could come up with a bunch of stoichiometry relationships or stoichiometric relationships. And let's talk about all the different ones we could get. And they are all based on the coefficients. Yeah. And obviously here nothing's written, so that is a 1, right? So we could say in this particular reaction, for every 2 moles of CO that I put in there, I will also need to put in there 1 mole of O2. And for every 2 moles of CO that I put in there, I will get out 2 moles of CO2. I could also say for every 1 mole of O2 that I put in there, I will get out 2 moles of CO2. These are all really the equalities that you could get from this equation. They clearly are not equal to each other in terms of 2 does not equal 1, right? They are equal to each other in terms of proportion of what you need to put in there to get this reaction to go, right? Like if you want to make a dozen cookies, you got to throw so much flour, right? So much eggs, some chocolate chips, all that good stuff in there, right? To get a dozen cookies. That's the proportion you need to put in there to get out a certain amount. Same idea here. That's what these are. Now, these are really equalities. And just like any equality, even though we just got it from the equation, we could write 2 conversion factors from each of them. So we could say in terms of our conversion factors, for every 2 moles of CO, there is 1 mole of O2, or 1 mole of O2 up on top, 2 moles of CO on the bottom, and that's from this guy. We come to this equality, we could have 2 conversion factors, 2 moles of CO over 2 moles of CO2, or we could flip it around, 2 moles of CO2 up on top and 2 moles of CO on the bottom. And lastly, for this guy, we could go 1 mole of O2 over 2 moles of CO2 are 2 moles of CO2 up on top and flip it around there, 1 mole of O2. So from this one balanced equation, we actually have available to us 6 different conversion factors that we could use. We are definitely never going to use all 6 of them. We are pretty much just going to use one. Otherwise, I think you might be doing the problem wrong if you start using multiple ones in the same problem. So usually we're just going to use one, and we're just going to choose whichever one that we need. But this is what I was saying before. This is really what stoichiometry is. It's really just a conversion factor. And like I said, instead of going to a table to find it, like, 12 inches of the foot, we actually use the equation as a source of where we find our conversion factors. And once again, all those numbers are simply just the coefficients from the balanced equation. That is why step number 1 in this process is you need to make sure the equation is balanced, because if it's not balanced, then all these conversion factors are going to be wrong, right? So that's always the first thing you want to do when you're doing these type of problems. So how would this work? Let's just make up a problem. We'll go through the 4 steps together, just to kind of show you what we'll do. So let's just say, for example, that we produced, in this case, we'll go with, why not? I'll go 105 grams of CO2. And we wanted to know how many grams of O2 did we start with? Okay, so we're going to go through the 4 steps that we just talked about. So the first step is we want a balanced equation, which clearly we have already done for us. So that's a good step. The second step is basically take whatever they gave you and convert it to moles. So the only actual number that they gave us was, we basically have 105 grams of CO2. So do I need to do that step? I do need to do that step, right? Because I'm in grams. I need to convert to moles. We know how to do that because we just did it, right? So I need the molar mass from the periodic table to allow me to do that conversion. So I'm going to go again to my periodic table. I'm going to find carbon, which is 1201. I'm going to find oxygen, which is 16. And I'm going to calculate the molar mass here of CO2. That would be 12.01 for my carbon. Plus, I'm going to try to do better than I did last time. 2 times 16 here for my oxygen. I'm going to try without the calculator, 4401 grams per mole. I'm going to hope for the best there. So that is 4401 grams per mole, which would be the molar mass of CO2. And we're going to use that again as a conversion factor. And again, we're just going to do a basic kind of stoichiometry problem, basic dimensional analysis. Grams are on top, so I need grams on the bottom. I'm going to do my 4401 grams per mole of CO2 in this particular case. So again, really, we're just kind of setting up our numbers so that we could actually do the stoichiometry part. We're really just trying to get it into the right units. So again, we're going to multiply and we're going to divide. And in this case, we'll take 105 divided by 44.01. And that's going to give me, if you get an answer, 2.3858. I'm just going to take it to a few digits. Moles of CO2. Right? First off, any question on that calculation? That's pretty much the same calculation we were just doing previously in this chapter. Now, if we think about where we're at now, we have now kind of set our number to the right units. Now we're ready to actually do the stoichiometry part. And the stoichiometry part is the third step of your process, which is you're going to go to the equation and find the mole to mole relationship that you need. And that is the big stoichiometry part. So clearly, one thing that I need is CO2 because that's what's given to me, right? So that is one thing I want to look at in the equation. The other thing that I want to look at is what I wanted to actually find. So in this case, I actually want to find O2, right? So I want that. So we did this earlier. The relationship between O2 and CO2 is right here. For every 1 mole of O2, that gives us 2 moles of CO2. That is the relationship, again, that we got from the equation. Nothing more than just the coefficient, the numbers in front of everybody. That gave us really 2 options to use for conversion factors. If you remember, it gave us this option here, and it gave you this option here, right? So we just got eliminated 4 of the 6 conversion factors we don't need to touch, right? We want to choose whichever one's going to work for us. So if we take the number we just got, which was 2.3858 moles of CO2, and I want to obviously get rid of the CO2, my CO2 should go on top or bottom? Bottom. That means conversion factor on the left or the right should I use? Yeah, I should use the one on the left as it has my CO2 on the bottom. Again, opposites cancel, right? Because we're just doing dimensional analysis. So we will use that as our conversion factor. And again, that comes from the balanced equation. And again, at this point, the moles of CO2 are going to cancel. We're essentially just dividing by 2 at this point. And we will end up with 1.19, we'll call it 3 moles of O2. That is our third step. And that is really the big stoichiometry move right there. Just kind of use the mole-to-mole relationship. Any questions on that? And again, this comes from the balanced equation, right? We are close to what we want. By the way, if I wanted my answer to be in moles, what should I do at this point? Just maybe put a box around it, right? And I'll be done with the calculation, right? So if I wanted moles, I am actually there, but I don't want moles in this case. I do want grams. So we do need to do the 4th step, which is we're going to take our moles and convert it to grams. The good news is we know how to do that because we've done it before. It's the grams to moles, moles to grams conversion. That again is the molar mass from the periodic table. I do need to be a little careful here because I am in what sort of units are at this point? I'm in grams of what? O2, right? I'm no longer CO2, right? Because I did that conversion. So I do have to go back to the periodic table and now get the molar mass for O2 because that is what I have. I can't use, obviously, the same molar mass that I used at the beginning. So we would go back to the periodic table and maybe I'll just do it. Yeah, I'll do it up here. O2. That's going to be 2 times 16 for the oxygens. And that will give us 32 grams per mole as our molar mass. And that's really going to be our last step here in the process. So we'll take that number we just got, 1.93 moles of O2. Again, we want to go opposite. So if it helps you to put the 1 over it, we got moles on top. So we do want moles on the bottom here of O2 and our 32 grams of O2 up on top. Again, multiplying, dividing, and our moles of O2 will cancel. So we're going to times that by 32 basically. And we're going to end up with 38.2 grams of O2 would be our answer. And again, it's the same 4 steps along the way. And it's always these same 4 steps for us that you should follow. I did get an answer after each step just to kind of show you each individual step. If you want to do it all in one calculation, you can as well and not get an answer in between. Or you can obviously get an answer in between and just keep going. So what this means is in this problem, if I had produced 105 grams of CO2, in order to produce that 105 grams, I would have had to put in there about 38.2 grams of oxygen to get out. Basically 105 grams of that product. Any questions on any of that there? All right, so I did one, so I think you should try one maybe. All right, why don't we try this one here? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed by the reaction of 5.32 moles of lithium with water? So we do want to start with the equation. So let's just kind of work through that together. Lithium is Li, right? Reacts with water, which I hope you know is H2O, right? 2,4 means an arrow. Hydrogen gas is a diatomic molecule, right? So that's H2. And lithium hydroxide, lithium is +1, hydroxide is -1. So it looks something like that. All right, you pick it up from there. Follow the 4 steps. We're going to balance the equation. We're going to convert to moles. We're going to mole to mole relationship. And then we're going to go from mole. Okay, let's take a look here and see. So obviously in this case, we have a stoichiometry problem. We're basically given, we got 5.32 moles of lithium. We're eventually looking to find moles of hydrogen. So again, we just want to kind of follow our steps. So the first step obviously is to balance the equation. This obviously is a problem where you had everything in words. So just like I did before here, I just want to make sure obviously just get the right formulas. It is not balanced currently, right? So we do need to go through and balance it, and maybe a 2 there, a 2 there, and I feel like I'm just putting 2's everywhere. Maybe a 2 there as well. See how I did. We got 2 lithiums on the left and right. That worked out not bad. We got 2 times 2 hydrogens on the left, which is 4. And we have 2 hydrogens there and 2 more there, which is 4. So that's good. And obviously we have 2 oxygens there, and that 2 goes to that oxygen. So we have 2 there. Not bad. Just throws out some 2's and hope for the best. By the way, everything with balance except for the hydrogen, right? So you could use the fraction like 1/2 for the H2 and then multiplied by 2 across, yeah, to get it balanced. So if you're not sure, you could have laid up in 1/2 there, and then that would have balanced it. Then you need to multiply the whole thing by 2 to get to where we got to. All right, now that we have it balanced, that is check. Next thing we want to do is take whatever they gave us and we want to convert it to moles. So this is the only number they gave us. Do I need to convert it to moles? I do not. It's already done for us. So good deal. Halfway through, right? There, that's a check mark. So the next thing we need to do then is really do the stoichiometry part, which is we're going to go to the equation and find the 2 things we're interested in. So one thing we're interested in is obviously whatever they gave us, which in this case is lithium. So we're definitely interested in this one. And the other thing that we're interested in is whatever we're trying to find. So in this case, we're looking for hydrogen, which is over here. So those are really the only 2 things we really should concern ourselves with in terms of this equation and stoichiometry. So the relationship that we have here, picking up with step number 3, because that's what we need to do, our mole to mole relationship. We could see from the equation that there are 2 moles of lithium will give us, and again, if nothing's written there, that's a 1 mole of H2. So that is the relationship that we could get from the equation. It's really, again, the conversion factor that we could get. That does give us 2 conversion factors. We could use 2 moles of lithium over 1 mole of H2, or you could flip it around, do the 1 mole of H2 up on top and the 2 moles of lithium there on the bottom. So we're ready to do that calculation. We're going to go 5.32 moles of lithium. And once again, if we put a 1 over it, we could clearly see, hopefully, our lithium is up on top. So remember, opposites get rid of it. And that's what we're trying to do. So I should use conversion factor on the left or right in this case? The right has the lithium in the opposite location, right? So we're going to use the one on the right. Going to give us 2 moles of lithium, 1 mole of H2. Once again, we're going to do our normal multiply and dividing. Again, setting it up this way, we don't even have to really think about what math we're doing, right? It should always be the same. That's going to get rid of the lithium, and it's now going to leave us moles of hydrogen, which is good. And that is the big stoichiometry move right there. So we're going to divide that by 2. That's going to give us 2.66 moles of hydrogen in this case. Yeah. Do I need to go any further at this point? What am I looking for? Moles of hydrogen. Yeah. So, you could put a box around it would be a good idea at this point. Yeah. We actually don't need to do step number 4 here. By the way, if we wanted grams, what would we need to do? We would need the molar mass of H2 at this point, right? So we would then need to take, if we needed to get to grams, which we did not in this example, we would have to go to the periodic table, get the molar mass of that. And I'll get you 2.016, I think, grams per mole. And we would, again, do that 4th step if necessary. But again, in this case, it was not necessary. So we really did not need to do the 4th step in this case. But if you needed to, that again would be the process to get yourself to grams, right? Any questions on that there? So again, what you want to think about is just those 4 steps and just go in order, like something done, just keep going forward. Don't go backwards. All right, let's try another one here. We'll do the exact same. Oh, bless you. Maybe. Yeah, we'll do the exact same equation. And we're in this time, though, we are looking for grams of hydrogen, but we are starting with 81.75 grams of lithium. So let me give you some numbers in case you can't see the periodic table. Lithium is 6.941. Hydrogen is 1.008. So give it a go. Again, just follow those same 4 steps. Balance the equation. Convert to moles. Mole to mole relationship. Okay, let's take a look, see how you're doing. So again, we're just going to follow our steps here. In this particular case, we have the same equation. We are starting with 81.75 grams of lithium. And in this case, we're looking for how many grams of H2 would we produce in this case. So step number 1 is a balanced equation, which obviously we did previously. So we're good on that. Step number 2 is we want to convert to moles. And in this case, we are given 81.75 grams of lithium. And obviously here we do need to do this step because we're not in moles. So we got to kind of get our number to the right units to really do the stoichiometry part, which is coming up next. So I would just go to the periodic table, look up lithium, and I can see that lithium's molar mass here from the periodic table, 6.941 grams per mole. And again, that's just going to be used as a conversion factor to go from grams to moles. So just dimensional analysis, grams are up on top, so we do need to go opposite to cancel. So the 6.941 grams need to go on the bottom, and a mole of lithium goes on top. Remember, again, with molar mass, the number stays with the grams, and it's always 1 mole on the bottom, or wherever the mole ends up. Again, we're going to multiply the top. We're going to divide the bottom. That's going to get rid of our grams, and that will do our first part here. Divided by 6.941. Looks like 11.778. I'll just take it to a couple extra digits, maybe, moles of lithium. Any questions on that so far? The next step really, again, is the big stoichiometry part. We want to do our mole to mole relationship. And again, that is from the equation that we find that. And we always just want to look for the 2 things we're interested in. So just like in the last one, we are interested in lithium because it was given to us. And we are interested in hydrogen because that is what we're trying to find. So again, we can just ignore pretty much everybody else in that equation. We just really want the mole-to-mole relationship between those 2. And from the coefficients, and that's all it is, no math involved in that, it's just take the coefficient. We see that for every 2 moles of lithium, just like it was in the previous problem, we get out there 1 mole of hydrogen. And just like in the previous problem here, we could have 2 conversion factors to choose from in our problem here. And again, they're just fractions, one on top, on the other on the bottom, and then flip it. All right, so we're ready to do that. We're going to pick up with our number that we got here, 11.778 moles of lithium. Once again, just going to keep it simple and go opposites cancel. So moles of lithium are on top. So just like the other day there, or the other one, we have our moles of lithium on the bottom on the one on the right. So that is the only conversion factor we're going to use. Again, you should not use them both. Otherwise, you're going to get in trouble there. We're going to multiply and divide. Again, moles of lithium going to cancel. And that's the big stoichiometry step that's going to take us from lithium, which is really not what we're interested in, to hydrogen, which is what we are interested in. So we're just going to divide that by 2. And that's going to get us a 5.88, I call it 9 moles of hydrogen. In this case, this is not the end of the problem. It would be if we were interested in moles like the last one, but here we are interested in grams, right? So we do need to do that additional step, which is the 4th step. And like I said before, as you can hopefully see, you will always be in moles at this point. So you're going to take those moles, in this case, back to grams. So once again, that's going to require the molar mass. But just like we were talking about in the previous problem, we are now looking at hydrogen here, not the lithium that we started with. So we'll go there to the periodic table and get the molar mass of hydrogen. That is 2 times 1.008 grams per mole, coming right there. And that's going to get us 2.016 grams per mole as the molar mass of lithium, not lithium, of hydrogen. And that's, again, just going to be a conversion factor here. So to finish this problem up, 5.889 moles of hydrogen. Again, hydrogen is up on top, so moles got to go on the bottom there of hydrogen to cancel. And the grams will go up on top. Again, when we multiply and then divide, go right to division thing. Those are going to cancel, and that's going to get us here. It looks like maybe 11.87 grams of hydrogen in this particular case. So hopefully you can start seeing a pattern here. It is just those 4 steps. It will get you to the end if you just follow them along the way. What does that number really mean? That number is what is sometimes referred to, since it is a product. This is what is known as a theoretical yield. A yield is a product. And what it basically means in this case is if you did this reaction and you put into this reaction 81.75 grams of lithium, if everything went perfect, there was like no side reactions, you weren't a klutz and spill something on the ground, you should, in theory, get out 11.87 grams of that hydrogen. And that's like your maximum yield. In reality, you won't probably get that. You'll get probably something a little bit less, but that was like the maximum amount of product that you could get. Any questions on any of those steps there? I am not, no. So we don't really cover theoretical yield or actual yield. Our percent yield is something that goes with that as well. So we'll just basically, he'll be asked like this, how many grams of like H2 would you produce or something like that. Now, in these last 2 examples, we did go, from this side of the equation to this side. And on the first one, we went this way. But just a reminder as well, you don't have to cross over the arrow to do this calculation. If we were interested in like lithium and water and the relationship between those, we could do a calculation between those 2 things. For example, we just figured out how much H2 we would produce in this case. We could then actually just do a calculation between H2 and this guy and figure out how much of the lithium hydroxide we would figure out as well. So sometimes people think when they do stoichiometry, it has to always like cross over the arrow and do it between something on opposite sides. You could stay on the reactant side and do it between 2 reactants, the same calculation. You could do it between 2 products. So you don't necessarily have to always cross over the arrow. And it's really just the same 4 steps if you stay on the same side or cross over. It doesn't really matter. Any questions on that there? All right, I want to take 5 minutes. Okay, we're gonna pick back up here. So hopefully you're starting to see again a pattern of the steps you should follow in these type of problems. Let's just try one more here to finish it out. If you started with 765 grams of C6H12O6 and it's consumed by the body, what is the mass of CO2? So we're really looking for grams of CO2 here. And I'm going to give you some information that might be helpful. 12.01 from the periodic table for carbon, hydrogen 1.008, and our oxygen 16. So see what you come up with. Again, same 4 steps, even though it may look scarier, it's still the same deal. So balance the equation, convert to moles, mole to mole, and moles to sum. Okay, let's take a look, see how you're doing. Again, I'm just going to follow the same steps. I see some coefficients here, so I feel pretty confident it's balanced. And if we do go through, it is balanced. And I would say in most cases, we do see coefficients probably balanced, but just make sure you take a look at it to make sure. In this case, we're off to number 2 here, which is convert to moles. And in this case, we are given 765 grams of C6H12O6. And we do need to do that. So again, we need to go to the periodic table, right? And that's going to get us our molar mass converted to moles. Once again, we're just adding up all the parts. So there is 6 times 12.01 for our carbons. There are 12 hydrogens at 1.008 grams per mole. Again, basically our carbons, our hydrogens, and our oxygen here. Which is 6 times 16 grams per mole. And again, that is all coming from the periodic table. And we will add all that together, 6 times 12.01 plus 12 times 1.008 plus 6 times 16. And it looks like we do end up with a molar mass of 180.2 again grams per mole. That again is going to be our conversion factor to basically just kind of again get our number in the right units. So we can't use them the way they are in grams or really any other unit. So we do have to get them over there into moles. So using the molar mass here as a conversion factor, this is basically over 1, which means when we use the molar mass, we do need grams on the bottom in this case. So 180.2 grams per mole of our C6H12O6. When we multiply the top and divide the bottom, that is going to get rid of those grams. And that will get us 765 divided by 180.2. Looks like we get 4.245 moles of C6H12O6. Any questions on that there? Now we're really ready for the stoichiometry part, now that we really got our into the right units to allow us to do that. So we're going to then do our mole to mole relationship. And once again, we're going to go to the equation and find the 2 things we're interested in. So in this case, we were obviously starting with this guy, but we eventually want to get over to CO2, which is right there. So those are, again, the 2 things we want to kind of look at in the equation. And we can see from the coefficients, for every 1 mole of the C6H12O6, we get basically 6 moles of the CO2. And again, that's going to be our conversion factor that's going to get us hopefully towards the end here. And if you helps you could write the 2 conversion factors, and that will give us our kind of 2 conversion factor option here. Or we could flip it around and go with 6 moles of CO2 up on top, and our 1 mole of our C6H12O6. So continuing on with our number from the previous step there, we got 4.245 moles of C6H12O6. Once again, that's on top and we want to get rid of it. So we will use the conversion factor on the right here that has it in the opposite location. And that again is coming from the balance equation where it says 1 mole of our C6H12O6 gives us our 6 moles of CO2. And that is the big stoichiometry part, again from the balance equation. The moles of the C6H12O2 are going to now go away. We're going to multiply it by 6 basically. And we will end up with 25.472 moles of CO2. Any questions on that part of it? Well, if we wanted moles, right, we would be done, but here we do want grams, so we do need to do that fourth step. So fourth step here is we're going to go from our moles to grams in this case. That again is going to require the molar mass, and in this case, we have now converted to CO2. So we again need to go back to the periodic table and calculate that, or remember that we calculated in a previous problem, I think. 12.01 plus 2 times 16 here for the oxygens. Gonna get us our 4401 grams per mole. So our very last step here is taking the number from the previous step, 25.472 moles of CO2. In this case, we need moles on the bottom using the molar mass and our grams up on top, so that when we're all done, the moles will cancel and it will leave us grams, which is what we're looking for. And again, we're multiplying here up on top always. So we're going to multiply by 4401. Going to yield you on your calculator 1121 grams of CO2. You know, if you're still sig figging at this point, maybe you should be. 1120 grams of CO2, really based off of the 3 sig figs off of that guy right there. That again would mean in this case, if we put in there our 765 grams of the C6H12O6, everything went great. We get about 1120 grams of CO2 should be produced. Again, a little scarier of an equation, a little bigger of numbers, but still the same 4 steps. So just follow those 4 steps, should get you to the end. Any questions on any of that there? All right, that wraps up this chapter 7. All right, so as we talked about last time, we are going to skip ahead here to chapter 9. We are not skipping chapter 8. I did post a recorded lecture for it. You are responsible for it. You got a couple of weeks before it's on the exam that you need to make sure you watch it. And that it will involve gases. That chapter 8, which is posted up online, would be the last chapter that's on exam 2 that's coming up. Yeah. So this would start exam 3 material here with chapter 9. But this should be helpful for the next couple of weeks of lab coming up. So we'll get into our solutions here. So we're going to talk about solutions, and solutions are really aqueous substances, and really aqueous is the symbol that we give to solutions, and that was what the AQ means. It is different, by the way, than when you see L. Yeah, L, which is liquid. So there is a difference between a liquid and something that is aqueous, which is a solution. A liquid is a pure substance. So for example, if you had just water, that would be a liquid. Now the aqueous guy, which is a solution and in the liquid phase, is actually a mixture. It's actually a homogeneous mixture of 2 things. So for example, if you took water, which is a pure substance, and you took some sodium chloride, which is a solid, and you put them together, that salt would dissolve in the water, and you would end up with a sodium chloride solution that would have an aqueous symbol next to it. It's actually made up of 2 things. It's made up of water and the sodium chloride, which is a mixture, right? 2 or more substances together. So a solution is actually made up of 2 or more substances. Now, the substance that is there in the smaller amount is what's known as the solute, and the one that is there in the larger amount is known as the solvent. So in our example here, the sodium chloride is our solute, and we're dissolving it in water, which is our solvent in this case. Water is a very good solvent for things that are ionic and things that are polar, which we'll talk about in just a second. But it's actually not a good solvent for some other things. So it's not always a solvent, but a lot of times it is. How do you know what the solute is? The good news is it's always the name of the solution. So a sodium chloride solution, sodium chloride is the solute. If you have a potassium chloride solution, potassium chloride would be the solute. So whatever is in front of that little aqueous thing is the solute. And if it is ionic, it's probably going to be water is going to be your solvent in most cases. But again, maybe not always, but water is a very common solvent. So again, that is the difference between those two. Even though they both are really in the same state, they're both in the liquid state, but one is really a mixture and one is just a pure substance by itself, like water. So here we have water and copper 2 sulfate. So water's our solvent here. Copper 2 sulfate is our solute. And when we mix it, we get this nice homogeneous type mixture, which is an aqueous solution of copper 2 sulfate in this case. Yeah. And again, that is typically what it would look like in that sort of scenario. Now, water, as I mentioned before, is a really good solvent for a lot of ionic compounds. And that is because, as we talked about in bonding, water is a polar molecule. And because it's a polar molecule, it has a side that is more negative and it has a side that is more positive. So water, which is this guy here, the oxygen side of water is more negative and the hydrogen side of water is more positive because it is a polar molecule. That uneven distribution of electrons overall gives it a positive side and negative side. And that works really well, for example, when you go dissolve something like a salt, like sodium chloride. When you dissolve sodium chloride in water, it basically will break up into its ions, sodium ions and chloride ions. Now, what happens with water and why it looks like, for example, it disappears when you make a solution, it's because water basically just surrounds those ions. So the negative side of water will actually surround the positive ion, and that's the oxygen side. While the positive side of water, which is the hydrogen side, will actually surround the negative ion. And that does two things. What that does is, frankly, it prevents you from seeing it because there's just a ton of water molecules all around those ions and it's no longer visible to you. And it also helps it obviously dissolve that way. Water also prevents the very strong attraction there is between the sodium ion and the negative chloride ion, that if the water wasn't there, they would want to come back and stick together. By the way, this is a mixture because if you took salt water, like you might have done in one of these labs, or maybe will, if you heat it up, what's going to happen to the water? Yeah, if I heat this water up or the solution up, all those water molecules are going to evaporate, right? And there's going to be nothing that's going to prevent those guys from coming back together. And you will see the solid come back. And mixture, right, is two or more things that keeps their identity. They don't change. You get the solid salt back. If you wanted to, you could trap the steam coming off, which is the water, right? And you could have both parts of your mixture coming back. This is actually a physical change. This is not a chemical change or anything like that when you make a solution. It's just a physical sort of property that's happening. So sometimes people think because it kind of disappears, like some type of chemical reaction occurred to make it disappear. So it's actually just a physical change that occurs in this case. By the way, this is helped along a lot because typically if you're going to dissolve something, you do what? You mix it, right? And as you're mixing it, what you're doing basically is throwing a ton of water molecules all over that solid. And you're also providing energy, which allows them all to break apart really quickly and start to dissolve a lot quicker than it maybe normally would be. And that's sort of what an ionic solid looks like. It's just this big thing of all those ions stuck together. And even though that's an extremely strong attraction, there's just so many water molecules that they're able to just pluck them off because there's just so many of them that kind of overtake that charge. And as you can see here, as you mix it, you're just going to start throwing a lot of water molecules on that with a lot more energy, and that's going to help in the dissolving process. Here's another picture in case you did not like the first one, and maybe a third picture in case you didn't like the first two. I'm out of pictures. That's good. All right, so let's talk a little bit about examples of solubility in water. things are soluble in water, and if they're soluble in water, what that basically means is they mix. And one of the major sort of ideas about things being soluble in water or just soluble in general is things that can interact with, say, water the same way water interacts with itself makes them very soluble in each other. So if you get two things to come together that they're both like working with the same sort of interaction that they do with themselves, they're going to have no problem interacting well with whatever you're trying to dissolve. You get two things that are using way different types of interactions, they're going to have a real problem when they try to come together. So any ionic compound, pretty safe bet, is going to be soluble in water for that reason, what we just saw there. What we just saw there is sometimes referred to as an ion dipole interaction, and basically it's a positive negative attraction. So how all molecules interact with each other is they interact with each other in a very simple way. They interact with each other in a positive negative attraction to each other, right? So we know positive and negative things are attracted to each other. So that's what we saw when we saw our ions, right, being surrounded by water. The negative side of one is attracted to the positive of the other. And that's really how all sort of interactions between molecules happen. It's actually a fairly simple thing. It's just like positive side of one thing is attracted to the negative side of another, and they kind of mix together really well. There are also non-ionic compounds that are also soluble in water, things like sugar or ethanol. So why is sugar or ethanol soluble in water? If we draw ethanol, for example, it looks something like this, and you'll be able to draw it when we get to organic, I suppose. So this is what ethanol looks like. And ethanol, like this organic compound, actually has kind of two parts to it. It has kind of from what I put in the box, those are all carbons and hydrogens and carbon bonds. And if you remember from bonding, all of those bonds are nonpolar. Carbon-hydrogen bond has a difference of 0.4 in electronegativity. Carbon-carbon has a difference of 0. Those are all nonpolar sort of bonds. So something like ethanol here actually has two sides to it. It has a nonpolar side, but what it also has, which is really important for how it's able to work well with water, is it has this side right here. And this side right here is the OH group. And that OH group is a polar bond. And that OH group, which is a polar bond, is more negative on the oxygen and more positive on the hydrogen because of the electronegativity difference between those two, like we talked about in bonding. It actually has this polar bond. And that is really good because even though most of this molecule is neutral, it has no charge, it has this one little part that actually has a charge, has a positive side and a negative side, which works really well when a water rolls through that also has a negative and positive side. That gives these guys a way to interact well with each other through one of the negatives to one of the positives. And this is a special type of interaction, which is known as hydrogen bonding. And that's because it's a bond between hydrogen and oxygen, nitrogen, or fluorine in this case. And that makes something like ethanol really soluble in water because they both have that like positive, negative way that they can interact with each other, and it makes it really soluble, and they will mix together in this case. If you take ethanol and water and they're both liquids and they are soluble in each other and you put them in a test tube, they all look like one thing, right? They all should mix together. You shouldn't see different layers, right? If something is insoluble in each other, you would actually see some different layering happening, right? So in this case, you would actually see something like that where it all just looked the same throughout because it all should be able to mix really well. Now, as we'll talk about when we get to organic chemistry, if by chance you don't have ethanol here, but you have something like octanol, which has about another like, it's got like another 6 carbons and a bunch of hydrogens. The solubility in water is non-existent because it gets too big and it blocks the ability of water to get to that OH part of it. So if you have things, for example, that are relatively small and has like an OH group or something that it can interact well with water, it will make them soluble in each other because basically they both are using the same type of interaction. Ethanol will hydrogen bond with itself. Water will hydrogen bond with itself. So when they come together, not a problem for them to hydrogen bond with each other. And they're able to kind of get in there to do so. Sugar is actually a little bit bigger of a molecule, but what sugar has going for it is it's littered with OH groups all over it. So everywhere there's an OH group on sugar, which is a little bit bigger of a molecule, it has a place where it can, same way, interact with water. And that's what makes sugar really soluble in water. When we put sugar in our water, right, it dissolves, right? Or sugar in our iced tea or whatever it may be, it does dissolve. So again, this is an example of methanol, which has just one carbon. But again, it has that OH group that can do that positive, negative hydrogen bonding and going to make it very soluble in each other. There's our ethanol also doing that hydrogen bonding. Now, what about oil and water? Oil and water do not mix, and that is because oil is essentially just a long old chain of carbons attached to carbons and hydrogens attached to hydrogens and hydrogens attached to carbons, really not hydrogens themselves. Hydrogens attached to carbons, and it just keeps going and going and going. Hence, like octane, right? You fill up your gas tank, right? And that's where we get all those things, just a big old chain of carbons and hydrogens. They break them up into lots of different things, and it produces different kind of things. But essentially, it is just a really long compound of nothing but nonpolarness. And when you have a nonpolar molecule like this, nonpolar molecules typically will use what is referred to as dispersion forces. Dispersion forces are the forces that a nonpolar molecule uses with another one. They are like the weakest type of force. And that is because something has to happen in order for them to be able to actually interact. And what I mean by that is if we look at something that's kind of a nonpolar, go here maybe, something that's a nonpolar molecule, it is essentially a neutral molecule. It has no negative side, it has no positive side, which makes it really problematic when it wants to interact with somebody else because it has no way to do that. So there are a couple of ways that things could happen, but basically it has to rely upon like electrons moving and like all the electrons deciding, hey, we're just going to kind of vacation over here to the left-hand side of the molecule. So if we had two nonpolar molecules and all the electrons in this guy decided to head to the left, and that happens, is polarizability to just kind of move over there temporarily. What that's going to do is temporarily cause a charge to occur in that molecule that normally doesn't have a charge. So we'll call this number one. So this nonpolar guy number one will now have like a charge that it doesn't have. It only has it because all the electrons decided to kind of go to the left rather than stay kind of evenly distributed. Now, what happens if that guy is still sitting next to our other nonpolar molecule is the electrons in this guy is going to go, cool, I'm like attracted to that positive charge you have now. And now that second nonpolar guy that normally doesn't have a charge will also gain a temporary charge. And now these two nonpolar molecules that started out with really no charge because of those electrons just kind of going that way now have charges, and they now have a way to interact with each other. And this is what is known as dispersion forces. This is what is known as an instantaneous dipole. It's a temporary, really weak one because what happens is we've all been on vacation and at some point we all have to go home, right? And those electrons then decide to go back home. And when they go back home, this guy will no longer have that charge. He's just going to pop back like that. And that's going to kind of weaken, obviously, and break that bond that he had with the other guy. And he's going to have to try to find a new sort of bond in the same way. So these are very weak and temporary type of things. You could also force this to happen by taking a nonpolar molecule and just rolling up on it a polar molecule, right? that also is going to cause those electrons to start to shift in that molecule because of the charges there. But again, it's going to be temporary because it's not going to be a really strong attraction, and they're eventually going to weaken apart. So this dispersion forces is typically what nonpolar molecules use when they interact with themselves and other type of nonpolar molecules. Like methane, which is a nonpolar molecule, it is typically a gas because it is held together by super weak forces. You just look at it wrong, it's going to be a gas. Think about a lot of organic things, butane, propane, those are all gases, yeah. And that's because they're all nonpolar and they're held together very weakly. A lot of organic chemicals, when we get into organic chemistry, and you may use them in the lab, you oftentimes will use them in the fume hood because they're very volatile, which means if you just look at them wrong, they're just going to go from the liquid phase and jump into the gas phase because they're not held together really tightly. And that's because the way they interact with themselves is a very, very weak sort of interaction. And that's really different than the interaction we see, like we see here on this slide, with polar molecules. Because polar molecules, no matter what you do to them, they will always have a positive side and a negative side because they have that unequal sharing of distribution. They are technically good to go out of the box. They have that charge. They're never going to lose it. They always have a positive side and a negative side. And that means when two polar molecules get together, there's not going to be a problem. They're both ready to go, right? The nonpolar guy's got to find a way to kind of get a charge, right? So it's not going to be able to interact well. And that's why polar molecules, when they interact with other polar molecules, they do what is referred to sometimes as a dipole-dipole interaction. And that's basically this interaction. The positive side of one is attracted to the negative side of another polar molecule. These are both like polar molecules. And they also can do what we see here, which is hydrogen bonding, which is a bond between hydrogen and nitrogen, oxygen, and fluorine. The key to know whether or not something can hydrogen bond is the hydrogen itself needs to be attached directly to an oxygen, nitrogen, or fluorine. That is why this hydrogen could hydrogen bond because it is directly attached to an oxygen. That is why this hydrogen could hydrogen bond because it is directly attached to a hydrogen. That is why none of these hydrogens, even though they're all hydrogens, none of those hydrogens can hydrogen bond because they are directly attached not to nitrogen, oxygen, or fluorine, but they're attached to carbon. So even though you have a hydrogen, it doesn't mean they're able to do that interaction. They actually has to be directly attached to nitrogen, oxygen, or fluorine to have the ability to hydrogen bond. The reason for that is nitrogen, oxygen, and fluorine are the most electronegative elements you can have, upper right of the periodic table. And that's always going to cause a polar bond and a separation of charge that's going to allow that to happen. Any questions on that there? So this is how ultimately solubility and how things interact with each other is how they use these intermolecular forces. And that's what these things are. Intermolecular forces, there's dipole-dipole interaction. Is dipole-dipole interaction, hydrogen bonding, and dispersion forces. And again, dipole-dipole and hydrogen bonding, that's your polar guys. Non-polars, dispersion forces. The strengths of these three is this is the strongest of all three. This is the weakest type of force. And the dispersion forces, which is the weakest, is what goes with non-polar guys. Hydrogen bonding is the strongest. Dipole-dipole is really strong as well, but hydrogen bonding is just a little bit stronger. Actually, hydrogen bonding is a type of dipole-dipole interaction that happens. All right, so this is again the way that they interact with each other and why certain things are soluble in each other and certain things are not. So when we get something like oil, they really don't mix because we have our oil, which is really large and trying to use dispersion forces, and we have water that's trying to use hydrogen bonding. And those two things don't work over the long period of time. So they can definitely interact with each other for a very short period of time before they're not able to maintain it. A good example of that, I don't know if it's a good example, but maybe something we've all done before, I've seen, like oil and vinegar salad dressing, right? You mix it. Yeah. Mixes for a bit, but when you put the bottle down, what happens? Everything separates out, right? And that's because oil is obviously non-polar, vinegar is polar. So for a short period of time, they could kind of get into each other and say mix. But if you just let it sit there, they will basically kind of mix out with each other because they cannot hang on to that interaction. In order to get something to dissolve in water, you basically have to replace water and water interactions with something that's very similar. And in the case of oil, it's really large and non-polar, so that's not so great. It's kind of like, if you have a small car, you can put it into a garage, right? Try to put a semi truck into the garage, it just doesn't fit right? Because it's like a little too big for where you're trying to park it, right? Maybe get a little bit in there for a bit, but not the whole thing is going to be able to get into the garage. And that's sort of the idea here. You can maybe get it to mix a little bit, but it's just not going to be able to maintain where it's at in that particular case. And that brings up the idea of when we talk about solubility of like dissolves like. And what that means is essentially if you have anything that is ionic and polar, you're good to go. Those things are going to mix. If you have anything that is polar and polar, they're also good to go. They're going to mix and be soluble. The thing that people sometimes miss is if you have something that is nonpolar and nonpolar, those things are also good to go. So nonpolar things are going to use dispersion forces. Other nonpolar things are going to use dispersion forces. That's the same interaction. They're going to be fine with each other. The only problem is you're going to run into some difficulties when you try to cross over polar and nonpolar. Not going to mix, going to be insoluble, and you're not going to get them to basically dissolve in each other. And that's the idea of like dissolves like. So if you can identify these two things as like being polar, you should expect them to mix. If you got an ionic thing and a polar thing, you should expect them to mix. And again, if you have two non-polar things, they should definitely mix. But again, if you cross over, that is why water is a really good solvent for a lot of things because it takes care of all ionic things and it will take care of all polar things pretty much. But if you try to use water with something like Br2 or Cl2, which is nonpolar, it's going to be a terrible thing to try to mix together because they're not going to mix together because one's polar and one is nonpolar. Any questions on that there? And here's a couple of pictures of what we were talking about. Up on top is sugar. And although it is a larger molecule, everywhere is littered with OH groups. And everywhere there's an OH group gives it an ability to interact with water. That's one of the things that can kind of compensate for something being larger is if you have a lot more OH groups, it just gives everybody a lot more places to interact. And it also increases the solubility. This is oil, like I mentioned before, basically non-polar all day there and going to have a really hard time there with water. This is typically what we see, right? If we put oil and water together, oil floats on top, right? You ever see an oil spill in the ocean, right? It just kind of floats there up on top. And usually the non-polar layer, when you mix it with something like water, is up on top. The water layer is usually on the bottom there. And again, at this interaction point here, there's a little bit of interaction happening, but if you mix this up, eventually it's just going to kind of move apart. Also, why, right? When you do oil and vinegar, like on bread, right? You pop the vinegar on it and on the oil, and you get this just puts like little spots, right, in there, the balsamic vinegar, right? And same idea because they won't mix, right? And your lava lamps. So when we talk about something being soluble, that means when one substance really dissolves in another, it is said to be soluble. And salt is soluble in water. When one substance does not mix with another, it is said to be insoluble. There is a limit to solubility, and it is basically temperature dependent. So at a particular temperature, there's only a certain amount of solute you can get to dissolve, say, in water. And typically, if you increase the temperature, you oftentimes will increase the solubility of a solid in water or something like that. So if you're having something that's really difficult to dissolve, sometimes you just kind of heat it up a little bit. It adds a lot more energy and allows that thing to be more soluble in that higher temperature than it is in a lower temperature. So a lot of times we'll just do that and sort of heat it up. Gases, for example, are always soluble in each other because gases are just flying around. So just by that process, they're all mixing together constantly as they are flying around. All right, we will lay it up there.